Okay, welcome to Simple Probability. The focus of this podcast, excuse me, is on highlighting some of the features or examples related to what you see ticked off here in green. This, of course, is a snapshot from your formula booklet. So the intention is to bring to life a number of these forms so you have a sense of what these formulae are trying to say. The only one that we will not get into today will be conditional probability. That will come later. So just very quickly, the difference between something like with set notation A union B, which in a probability context is going to be equivalent to the probability of event A or B, and then A intersect B will be equivalent to a stricter consideration of the probability of the events A and B happening. So keep an eye on that. Language-wise, the or versus the and makes a subtle difference at various times. So let's consider something like a really straightforward example. By the way, it's called simple probability, not necessarily because it's so easy, but it's different from conditional probability, and we'll see that later in another podcast. So let's say we're given a universal set. Looks rather menacing in terms of the denotation. It would be the set whose members are x, such that x is between 1 and 15 inclusive, as long as x is an integer. And then we have sort of subsets within this so-called universal set. Set A is 1, 3, 5, 7, you get the idea. And set B would be the multiples of 3. That would be 3, 6, 9, 12, and 15. And of course, there's some overlap of the numbers that I just said there in set B relative to set A. And so a number is selected randomly, or if a number is selected randomly from this universal set U, we'll explore all of these very brief sort of mini questions in just a second. A nice way to model the system is to introduce the idea of a Venn diagram. It is a nice way to actually visualize the setting. Not a requirement, but can be a good way to model the setting in some settings, and can also possibly get you maybe a method mark when it comes to some kind of evidence of methodology on an actual paper. So you've got sets A and B, and there's some overlap, right? So the universal set would be modeled by the whole box you see here. And as you start to look at 1, 3, 5, 7, the elements, if you will, in set A, those elements are clearly represented well in the system. And there are some overlaps, namely 3, 9, and 15, that belong in B as well, because these three numbers are not only in A, but they're also multiples of B. So you can start to separate out what's going on, and of course what's left over and does not fit in either A or B is still within the universal set. So that can be a nice way to try to get a sense of clarity when it comes to answering some of these questions here. So this notationally just means the number of elements in a set, which in this case in set B, you've got clearly these 5 elements in terms of being easily able to see that. And the probability, if you were to randomly select a number of it coming from set A, well, you've got the 1, 2, 3, 4, 5, 6, 7, 8 of those out of the possible 15, because it's 15 total in the set. That's pretty straightforward. And the probability of what's called not B, or B complement, here are the elements obviously in B, so everything not B is outside of that modeled realm right there, and that would be, of course, the other 10 elements, which not a bad idea to reduce to a number like 2/3, and we'll note that this value of the elements not in B, and thus the probability of getting those, is actually 1 minus the number that are actually in B. So 1 minus 1/3, of course, is the same as the 2/3, so you got that the probability of not B is just the complement, or 1 minus the probability of B. And that starts to bring to life this complementary idea, and we'll see pretty consistently that the sum of probabilities have to be 1. So let's say you randomly reach into the system here to pick out a number. What is the chance of getting a number from A or B, right? That's anything that's in this highlighted realm here. So there's 10 elements out of the 15. That's pretty clear because you're not talking about these 5 here. That reduces to 2/3. And that happens to be, if we start to bring to life another formula that's in your formula booklet, if you were to say, okay, there's 8 elements out of 15 in A, and there's 5 elements out of the 15 in B, well, you don't want to consider the likelihood of these happening twice, so that's an overlap, so you actually subtract out those 3 because they're accounted for over in this set as well as them being accounted for over in this set. So by virtue of subtracting them out, you're actually subtracting out what is the intersection of those. So that starts to bring to life one of the other formulae in the formula booklet, that the probability of A or B is the sum of these two, subtracting out the overlap that you can't account for, that you're not allowed to account for twice. So what about the probability of not A union B? So if I'm not in A, I'm 1, 2, 3, 4, 5, 6, 7 elements, or I'm in B, I'm these guys as well. So there's those 7 plus the 3 more that you're allowed to pick up that are loosely still in B. So you've got 2 out of 3 in terms of the reduction of that. Finally, the probability of A intersect B, the not of that. Well, it's pretty clear that the intersection, hopefully it's pretty clear the intersection between these two sets is right here. And so everything that is not that would be the remaining 12 elements. And so that is starting to give you some sense of how to interpret the notation. Okay, you'll hear the word unbiased sometimes in IB questions, which really just means that it's fair. In this case, an unbiased coin is tossed, and either you're going to get a head or a tail, and a 6-sided die is rolled. Die is, of course, a singular of the word dice, which is plural. So let's determine the probability of obtaining a head on a tossed coin and an odd number on the roll of a die. We should note that these events are said to be independent. That means that the outcome of the one event has no bearing whatsoever on the other. These outcomes do not affect each other at all. They're completely independent. A useful model here, in terms of methodology on a paper in particular, could be to try to flesh out some kind of a so-called possibility space, right? So you've got a matrix kind of an approach here where the coin either shows up head or tail, and the die, of course, any one of these 6 possible numbers. Well, in terms of the odd number requirement on the roll of the die, that's a 1, 3, or a 5, and obtaining a head on the tossed coin, well, you can see that you've got 1, 2, 3 possibilities out of the 12 possibilities total, right? Because 2 times 6 is a field of 12. So 3 out of the 12 reduces to a fourth. That happens to be 1/2 times 1/2, which is actually the chance of getting a head, right? 1 chance out of 2. And the chance of getting an odd number, which would be 3 out of 6, reduces to a half. So here we see brought to life the formula for independent events, namely that the probability of A and B is just going to be the product of those two. Example 3 deals with a card being selected from a so-called standard pack or deck of 52 cards. Not sure culturally if you're familiar with this. IB tends to not go with something that might be a little bit too culturally dependent. However, let's just use the basis for you've got suits, hearts, spades, diamonds, and clubs. You don't really need to know that, but there are in a standard deck or pack of cards, there are 4 suits, and then there are the cards 2, 3, 4, all the way through eventually 10, Jack, Queen, King, and an Ace. So there's 13 cards, 4 suits, there's 52 altogether. So let's determine the probability that a card selected will either be a heart or a blackjack. The or being that we're talking about finding the probability of a heart or a blackjack. And so if you kind of model this, you've got 13 possibilities of that card being a heart, and then here's a blackjack, the jack of spades, and here's a blackjack, which is the jack of clubs. So there's actually 13, 14, 15. You can pretty easily add up and see from this overall possibility space that there's 15 out of 32, right? So these events are said to be mutually exclusive, which means the one outcome excludes the possibility of the other. So if you're getting any one of these hearts, that excludes the possibility of a blackjack, or vice versa. If you're getting a blackjack, that excludes the possibility of a heart. That means they are mutually exclusive. Here's a case where we're non-mutually exclusive. Same setting, a card is selected from a standard deck, and let's find the probability that the card selected is more loosely either a heart or a jack. Well, here's all the possibilities of hearts, the 13, right? Here's the possibilities of a jack. There's actually 4, but here's a little bit of a snag because of non-mutual exclusion. There is this overlap, right? So there is this idea that in terms of the language here, the one outcome includes a possibility of the other. So because of this overlap, you want to actually subtract him out. But another way to look at it, at least from a modeling point of view, is you've got 13, 14, 15, 16. So that's going to be our answer. How do you get it? Well, you could just say it's the probability of A, the 13 out of 52, plus the probability of B, which is the 4 out of 52, and then you subtract out that one problematic overlap because you can't allow for the doubling of that. So that again brings to life one of the formulae in your formula booklet.